All right, so we've just had our first quiz of the semester. I didn't see a lot of smiles, and so my quizzes are never fun. No, there's a smile. All right. So now I feel good. The next homework assignment that you've got, the precipitation assignment, that's going to be due a week from today. I'll give that to you a little bit later once we've covered some of the things today. As per usual, submit that on MU Online, and then I'll post the grades and the solution to that shortly after your submission. Now, we started the semester with a little bit of hydraulics stuff, you know, talking about flumes and culverts and sizing of pipe networks. And there's a transition between hydraulics and hydrology, but today we're going to start focusing more on the underlying science of hydrology. And that's one of the challenging things that sometimes engineers get a little bit uncomfortable about when they're learning hydrology is you're maybe used to doing a lot of design and calculations. And you think of the basic science classes that you took as something in the past. You know, when you were a sophomore, maybe is when you did chemistry or physics. But hydrology is a science, and so a lot of the information that you have to learn is just not necessarily going to be calculation related or design-based or even analysis. And so understanding the terms on this handout that I've just given you, I feel is every bit as important as being able to plug numbers into a partial flume equation, or being able to draw using StormCAD to draw a pipe network and run the analysis. And so, you know, the concepts are the things that can persist much longer than, you know, familiarity with which version of StormCAD you just most recently used. And so I just wanted to emphasize that that's kind of the next several lectures are going to be science-based, and we will get back into application and problem solving when we're doing hydrologic modeling. But for now, our attention is going to be turned towards just understanding things like why does it rain? All right, but before we answer that big question, why does it rain, let's take a top-level view of what happens when it does rain and where the water can go. We want to reduce the runoff that gets into natural streams because of the scour potential and the environmental damage it can do. And three of the options that are available to us in order to limit how much water gets into the environment or how much water ultimately gets to a wastewater treatment plant if it's a combined storm sewer like it is in Huntington. We've got local disposal, which is a way of trying to reduce the runoff volume. We'll look at a picture of local disposal just to illustrate that. Inlet control, which is a way of, instead of letting the water go downstream very quickly, just holding on to it as close to the source as possible. Because if you're holding on the water close to the source of where it's being generated, then it doesn't have a chance to accumulate all in a big flash at one central location. And that's harder to deal with when it all concentrates to one spot. The problem is kind of amplified. So an intermediate step between storing the water at its ultimate destination and storing it at its source is on-site detention using ponds like we discussed last week. So local disposal, remember we watched the video of that water going into the porous concrete? That's an illustration of local disposal of water, making changes to try and reduce the impermeability of surfaces and allowing the water to infiltrate rather than to run off. So inlet control, by contrast, isn't necessarily increasing infiltration, but it could be a storage facility under a parking lot that's just holding onto the water temporarily and close proximity to where it's generated, and then over time it's slowly metered out into the drainage network. And that's what they have at the new practice facility here on campus. And then inline detention is the theory behind that big Japanese facility that we saw the video of last week. They have that in Chicago as well, a series of vaults throughout the city that water is directed towards during heavy storm events. And it's just an intermediate storage between the source and destination. And our last opportunity to equalize the flow before it has the potential to wash out a wastewater treatment plant is called a detention or flow equalization basin. And if you've already taken a wastewater course, you may know that it's bacteria and biological processes that we rely on to improve the quality of wastewater. And those processes operate a little bit slowly. We can't just instantly create more bacteria and expect them to be treating the water at a low flow rate at night and at a high flow rate during the day. It takes a while for them to become established. And so we can't have huge variations in flow rate coming to the wastewater treatment plant all at once. And so flow equalization basins are a little bit like a pond. And you did pond sizing in the homework that you submitted today. A similar volume accumulation increment step is used to size and analyze flow equalization basins at wastewater treatment plants. All right. Well, let's look at some pictures of what happens when there's too much water. We had some good illustrations of that here in West Virginia last summer. All of these next few pictures are taken from floods in the state of West Virginia. Obviously, it causes a tremendous amount of disruption to people's lives. It damages their property. It interrupts their employment. Entire communities can become isolated and cut off from the rest of the state, and so food supplies, water distribution, electricity, all of the necessities that people need for an ordinary life get cut off. And it can take a long time to recover from that kind of an interruption. So obviously hydrology is important in climates that are considered wet, like in West Virginia. Here's a picture of downtown Richwood during last summer's storm. We're a little bit pressed for time, so we won't watch this video of, maybe some of you already saw it. It's someone was taking with their mobile phone a picture of a house as it was floating down the river, and the house was on fire as it was floating down the river. So you know things are bad when not only is your house on fire, but it's also being swept downstream simultaneously. You know what? Let's watch it. We'll make time. We got to make time for the important things in life, like amusement with other people's misfortune. Oh boy. All right, so here it is. The house is on fire as it floats downstream. I don't think there's anybody in that house. I think they got out. It was saying on the sign there. What? I think you're right, yeah. White Sulphur Springs area. Yeah, it hits the bridge. I wish they would have left the video running when it hits the bridge, but they cut it off. You don't know, did it go under? Bad stuff, right? All right, well, hydrology isn't only important in wet climates. Hydrology is important all over the world, including in places where we usually think of as being very arid. Here are some pictures that I took in the various times that I've been over in the Middle East. This is on the eastern coast of the United Arab Emirates on the Indian Ocean. There's a very wide trapezoidal channel coming out of the mountains because when it rains in areas like this where the hillsides don't have much vegetation and it's a lot of rock which is fairly impermeable, the rain will concentrate from all of these different tributaries into a huge flow that they just direct out towards the ocean. And so although water is scarce there, there are some cases where they're not able to trap it and try and make some use out of the water. There are other places in the UAE where they've constructed groundwater recharge dams, and they are able to make a beneficial use out of that water. This is in an area that has lots of really nice farms, and so the water there will be pretty much used up by early summer, but in addition to allowing for agriculture in the local area, it also helps to recharge some of the aquifers that have been so heavily overutilized over the years. Here's another dam that's built in the UAE, and this is out towards a site that I was doing research on last year, and I really miss going out there, especially in January here in Huntington when things are dead and not so nice. I think about the pleasant walks I had out in the desert in the UAE. It'd be 75 degrees, and I'd go check my stream gauges and see how things were doing. Very nice. But when it rains, there can be a lot of property damage. When people think this is an arid area, we don't necessarily have to worry about rain. This is a parking lot where some really expensive cars got completely submerged and essentially ruined. And so property damage, interruption to life. You can see that a lot of people don't own raincoats in arid areas, so that when it rains, you just use what you've got. And that may be a trash bag as you walk around. Instead of a taxi, maybe these guys could have used a boat. Lots of flooding, and in some of the parts of the UAE, they have the same problem that we do here in Huntington. In Huntington, we have an inadequate drainage network. Well, there are parts of the UAE that also have an inadequate drainage network, and their solution to that is a series of trucks that will go to low-lying areas like intersections or underpasses for a freeway, and they'll pump the water out, and then they'll discharge it into the desert. And this is a case where one of these trucks ran into another truck, and it was a pretty spectacular accident, I assume, just based on the fact that the front part of the truck is completely missing. Let me ask you this. Why would this be a potential safety risk to have standing water? Okay, yeah. Okay, yeah, those are the two things that I was thinking of. Is number one is that insects and mosquitoes in particular can breed in standing water like this. But then also think about a car coming down the road. It's easy for people to become distracted and not necessarily pay attention. And so if two of your wheels are in the water and two of your wheels are on the pavement, that's going to instantly cause you to swerve towards the edge. And so it's very dangerous, and there needs to be a drain here in this location, and there needs to be a drain here. This is on campus where I was last year, although the picture is from a couple of years ago. If you drive through there, you can damage your car. My son, who at the time was only about 1.5 years old, broke his arm during one of these rainstorms. And so, it was a little bit scary, wondering if I was going to be able to get him to the hospital. We didn't go this way. There was sort of an alternate route that hadn't flooded yet, so we got him to the hospital eventually. But drainage has real-world consequences. This is part of campus over there in the UAE. And this is all a really nice quality polished granite. And it's beautiful, except for it becomes very slippery. And when I'm over there, I dress up a little bit more than I dress here in the U.S. I just wear Converse, but over there I wear like slippery dress shoes. And so if you're wearing slippery dress shoes and it's raining on polished granite, it's easy to fall down, and so you got to be careful in wet weather. All right, so let's think about the relationship between hydrology and hydraulic engineering. In hydraulic engineering, where we're trying to size systems, we're trying to figure out the size of pipes or channels or ponds, hydrology gives some answers that are needed at the beginning of the design process in hydraulic engineering. And so hydrology will tell us at the surface how much water there is and where it is. So by distribution, we can actually mean two things. Temporal distribution, which is over time, how is it spread out, and spatial distribution, which is over a variety of locations, where is the water. And so those are two really important things that hydrology tries to find out, is the temporal distribution of water, like a hydrograph, tells you the when of a peak, when it occurs. And then a lot of our analysis will be focused on trying to predict where there's going to be flooding, whether it's along a stream, where we know the slopes of the stream. Subsurface hydrology, which we'll only have a small exposure to this semester, looks at the movement and quantity and quality sometimes of water beneath the ground surface. And so there's a close relationship between surface and subsurface hydrology, because whatever doesn't go into the subsurface is still at the surface to flow around. But of the two, we'll spend most of our time this semester talking about surface hydrology. So the Q, the flow rates that a hydrologic analysis develops, are what are used in order to size pipe diameters and to size a culvert or a flume or a channel or a pond. And so that's what this arrow means, that the information and the output of analysis from hydrology is the starting point of hydraulic engineering. Any questions about that idea? All right. There are dozens of figures similar to this describing the water cycle. And maybe you even remember something like this from when you took earth science back in middle school. You know, like the water evaporates from the oceans, and then there's rain onto the ocean and onto the surface. What I like about this figure is that it kind of gives a conceptual description of some of the important transport mechanisms, so that it's showing during infiltration, that's the precipitation that turns into groundwater flow. Some of the groundwater ends up in lakes. Some of it ends up going straight back into the ocean. It's differentiating between evapotranspiration and evaporation. So evaporation is just from a free surface of water, whereas evapotranspiration is when there are plants involved respirating the water. Here in sublimation and desublimation, it's talking about the exchange of water that's bound as ice into the atmosphere. And the only other thing that I wanted to point out is that there's a huge amount of, a huge variation in the quantity of water that makes it from one place to another. And so this figure is similar to the one that we just looked at, except for that it provides a relative amount to help you understand, for example, for every 100 units of rainfall that gets onto the land, there are 385 units of rainfall that go onto the ocean. And so if we're just thinking about how much water is there in the world and where is it at any given time, the majority of the water is in the ocean, and the majority of the rain is falling on the ocean. And so what we have to worry about is only a small fraction of all the water that's out there. And if you really want to pinpoint some of the lowest flow movements of the water, you can see that of those 100 units of precipitation that fall onto the land, only one of those end up as exchanged between groundwater directly back into the ocean. The majority of these 99 units of precipitation are either going to evaporate or result in surface outflow from the land surface back into the ocean. And so the ocean is the ultimate sink of all precipitation eventually. And so are there any questions from this figure? Yeah, this is more of like a conceptual. I mean, it's numeric, but you'll notice there's no units here. And so I think it's normalized just to the percentage of precipitation that falls onto land. And it would vary a lot from place to place as well. You know, if we talked about how would a figure like this in Morocco be different from a figure like this in Brazil, there would be huge differences. And so I think this is just meant to represent the Earth as a whole, you know, averaged over the entire surface. All right. So on the idea of where is the water, 96.5% of all of the H2O on our planet exists in the ocean. And that's not really very useful to us most of the time. There's only a handful of places in the world where they have the expertise and the economic strength to turn ocean water into fresh water that can be consumed. There's not very many places in the U.S. that do it. In Florida there's a little bit, in California there's a little bit, But throughout the Middle East, they have to desalinate seawater, and it's very expensive to do that. It's highly energy intensive. It makes the cost of producing water anywhere between 4 times to 10 times as expensive as if you can just utilize groundwater or fresh water that's at the surface. And so of that fraction that's the water that's not in the ocean, so if we're just talking about the fresh water, most of the fresh water is tough for us to use because it's in isolated locations like the polar ice caps and glaciers. And you know, with the exception of maybe a few specialty vodkas or something that are claiming to have glacier water that's been, you know, extracted from someplace, almost all of the water that we consume is groundwater that's pumped up from below the surface or surface water that comes from lakes and rivers. But you know, each one of these bars just represents a successively smaller fraction of the overall supply of water that exists. And so here, this one is showing of the surface water, most of that is existing as ice and snow, and so a small fraction of the fresh water is usable in lakes. This groundwater is kind of a little bit misleading because it makes it seem like, oh, there's a fair amount of groundwater that's available, but some of it is so deep underground that it's not economical to pump up to the surface. And then another big part of the groundwater that's maybe not necessarily useful is it's in isolated geographic areas. And so the groundwater in Siberia, for example, there's lots of it, but it's not going to be very useful to where people are located because the population density in Siberia is so low. And there also happens to be plenty of existing freshwater resources in Siberia or Canada. And so the groundwater that we depend on, there's a lot of places where it's the groundwater tables are getting lower and lower because we're usually using those resources faster than they can naturally be replenished. Okay, part of being able to understand the movement of water through the environment is having a good conceptual understanding of a watershed. And there's a few different names that we can use for a watershed. Sometimes it's called a catchment or a drainage basin. In the UAE, they call them wadis. Probably lots of other places across the Middle East. But what I wanted to do was just show you a way of seeing a drainage basin using a free program, Google Earth Pro. I'm sure some of you have used Google Earth before. I've got it installed on my computer. And we'll pull it up here. All right, where is it? All right. So this is here in Cabell County. I live out in Ona, sort of the middle of nowhere, Ona. So if I zoom in on an area that I'm familiar with, I know this farm here. All right. The terrain is turned on right now, where what it's doing is it's taking an image and it's trying to add some three-dimensionality to the underlying elevation data. You know, if you hover your cursor over a certain location with the terrain turned on, you see how down here in this screen it's saying what the elevation is of the cursor. And so I can tilt my view of a location by pressing and holding down the mouse button. And so let me go over here. All right. So there's a depression here that you can kind of see as I pan through. It's like a V-shaped catchment. And if you stop moving, it's harder to see where the ridge lines are. But if we pan around, you can sort of see that, you know, here's the top of the hill. Any rain that falls to the left is going to flow away from this catchment, but anything that falls to the right of that ridge line is going to get down into this basin. And all of this basin is draining right into this guy's backyard. Actually under his house. I'm not sure why he picked that location to build his house, but yeah. So everybody sees what I'm getting at, that there's a ridge line here. It's the high point in the elevation that defines whether the water is going to go into the watershed or away from the watershed. Later in the semester, when we start using some watershed modeling programs, it's going to automatically draw lines around watersheds. We won't have to manually go in and look at them or try and measure the area, because the program can do that in an automated way by comparing the elevation of each cell to the elevation of a cell next to it. And it will kind of interpret flow paths. So inside of this basin, you'll notice that streams form. Why does a stream form in the location that it does? Like, why is a river here instead of there? It's the lowest point. And over time, that lowest point becomes sort of like a self-reinforcing phenomenon where, because the water is moving, it's sweeping some of the sediment, it's scouring, there's erosion, and so it becomes even lower. And then the area that's next to it, some of it will collapse in. And so these catchments get deeper and deeper and deeper over time. The hill will also erode because the wind is going to be blowing over it, and there's soil erosion as the rain falls on it. But that nested hierarchy is important when we talk about hydrology, because sometimes where we point to as our location of interest may have a very small upstream area, and so this is showing there's a small contributing area if we picked a spot on our stream that only has a couple of small creeks upstream of it. But if we, for example, put our point of interest indicator on the Ohio River, there could be hundreds of square miles upstream of a certain location, and all of the water that falls onto the surface has to be considered upstream of that point. So there are these nested smaller basins that all form larger basins. And how much water we get at an outlet, and outlet is a technical term that you need to understand. It's not actually like water coming out of a pipe. Instead, the word outlet just means a point where there is some upstream area that the water is concentrating to. So I could say, here is my outlet, and I'm just pointing to a location on the stream that's no different from anywhere else. We could have any one of these spots be an outlet, and we're just saying, I want to delineate what's upstream of this point of interest. And so it may be that there's a road crossing a stream here, and I consider this as my outlet location because I have to put a culvert there. And I'm trying to find out how big is the watershed upstream of that location. And so outlet, it means something conceptual rather than something physical. It may be indistinguishable from any other spot in a stream. But how much water comes to the outlet obviously is going to depend on the size, so that you're going to get more flow when you've got a big upstream area compared to a small upstream area. But that's not the only factor. There's some other ones that really matter a lot, such as what's happening inside of the watershed. So watersheds that are heavily urbanized are going to have more runoff and faster runoff than those that are natural and have been undisturbed by human activity. Soil type plays a role, and here in West Virginia, our soils have a lot of clay in them, and clay doesn't absorb water as well as sandy soils do. And so that plays part of the role in why we see such flashy storms, is that the water doesn't infiltrate like it would if we had different soil types. The terrain conditions, like sinuosity of the streams. And sinuosity simply means how windy are the streams. And if the streams are really windy, then that can delay the flow compared to streams that are relatively straight and uniform. In Florida, they have a lot of dredged canals, and the water can move through those canals more quickly than it would have if they were meandering streams. Terrain conditions also includes the slope of the watersheds themselves. Like A steep watershed is going to, for the reasons we've already talked about, water is going to infiltrate less because it's moving over the surface more quickly. And of course, rainfall intensity, the amount, the distribution, and rainfall intensity changes as a function of location. We're going to look at a database that's online where you simply pick a point on a map and that will characterize the rainfall intensity for you based on past historical data and on some statistical regressions that it does in the background. All right, well, understanding rainfall in part depends on understanding the movement of air, because when it comes down to it, what causes rain is air being lifted, which is a strange thing. But air being lifted causes rain, and so we have to know, why does air move around in the atmosphere? It's partly because there's temperature differences. It's partly because the Earth is spinning. There can be heat differentials. And you've probably heard of people describing a low pressure system or a high pressure system, and so those different systems moves air around. One of the big effects, the Hadley circulation, is simply that at the equator it's warmer because there's more solar radiation at the equator compared to at the poles. And so there's this tendency for the air to rise when it's warmer, and for it to fall where it's cooler. And so think about at the poles, at the North Pole and the South Pole, the air is coming down from the higher atmosphere because at the poles it was rising. And so if you have rising air someplace, it has to fall somewhere else. And so there's this kind of conveyor belt, you can think of it. Now it's in 3 dimensions. This is a sphere. So think about a layer that goes all the way around it that's constantly turning over from the equator towards the poles. That's Hadley circulation. That's partly responsible for the typical patterns we see. Another harder to understand effect is the Coriolis force. Now I've got an animation here at the top of the screen showing what happens if you have, think of a plate that's spinning. Maybe it's on bearings or something, but you release a marble, and as it goes downward on that plate, it's actually tracing not a straight path on the plate itself. So I'm going to let that play a few times while you think and understand what's happening in that illustration. One's a top view and one's an oblique view. So why does this matter again? All right. It's because in the Hadley circulation, that's what's causing the movement from the poles towards the equator. So that's kind of what this marble is illustrating, is the movement from the poles towards the equator. But as it moves down on something that's also rotating, our Earth is rotating, then there's sort of like a sideways movement. And that's what sets up these side-to-side, the westerlies in the northern hemisphere, where we expect our weather to be coming from the west towards the east. I mean, we just take it as a given that the weather they're having in Indiana today is the weather we're going to have in West Virginia tomorrow. But why is that? Why is it that the weather is usually coming from that direction towards us? Why doesn't the weather usually go from West Virginia towards Kentucky? It generally follows that pattern because of the Coriolis force combined with the Hadley circulation. So mariners have known about these trade patterns, the trade winds, for a long time. There are places at the equator called the doldrums where there are just long extended periods of no wind patterns, and ships would get stranded in the doldrums for weeks and sometimes months at a time. So understanding how air moves around is important to us, mainly because air movement causes precipitation. So here is a diagram of the general circulation of air on our globe. There's some strange names for these, the horse latitudes. I'm not sure why it's called the horse latitudes, but there's a Doors song that's called the horse latitudes. So, movement of water across the environment. This is an interesting figure that I took out of our text because it illustrates that water that evaporates in one location may get moved around across the globe quite a lot because of the air movement. So the black cell is representing where the source of the water was, and so this is down in South America near Colombia and Venezuela. There was some evaporation that they were able to trace from that location and then try and find out where was it measured when there was precipitation, and those are the light gray cells that show where it ended up. And they did a similar thing here in Thailand and Vietnam. The source of the water, and then that water this wasn't multiple cycles, this was just in one cycle, ended up as far away as the east coast of the United States. And this is part of why we have to be concerned with environmental pollution, is because a contaminant that's released in China may make its way to the United States, or acid rain from the eastern United States ends up in Canada or ends up in Sweden, and they've had problems in both of those places due to industrial emissions from North America and from England. So water moves around. All right, so I've already told you the big idea with the formation of precipitation is it comes from air rising. When air rises, it causes precipitation. But we can break it down into smaller steps to try and understand the background of why that rising is causing precipitation. Part of it is that when air is rising, it's cooling off. You probably know that at high elevations, there's lower air pressure. That's why sometimes when people are climbing Mount Everest, they have to wear oxygen masks, or if you're in an airplane, they say maybe that those emergency masks could come down out of the ceiling. It's because the air pressure is low at high elevations. So air that's lifted expands because of the lower pressure aloft, and as it expands, it cools. That cooling changes the percent humidity of the air until the air becomes supersaturated. As the air becomes saturated, that extra moisture has to go somewhere, and so it condenses onto nuclei like particles of dust. And then as those particles collide, they can form droplets that get increasingly heavy and can't be suspended by the movement of air molecules. And then ultimately that water vapor continues to grow until the water droplets are so big that then they fall downward by gravity. Now, as they're falling downward, most of the time they'll evaporate again before they hit the surface. It's only when there's enough moisture in a certain location that the air that it's falling through doesn't absorb all of the rain before it hits the surface. All right, so this is that process I was talking about just a moment ago of air that rises is surrounded by lower pressure air. So as we go up through the atmosphere, pressure is decreasing. So this first blue balloon is meant to represent a parcel of air. If you had some volume of air, it could even be an actual balloon, like a weather balloon or something. If you release that balloon and it's rising, the balloon is going to get bigger and bigger. And sometimes they send weather balloons up to try and measure things like air temperature, but they don't fill them all the way with helium at the surface. They have to leave enough slack space in those balloons so that when they rise, they can continue to expand. Because you can see as you get higher and higher in the atmosphere, because the pressure of the surrounding air is lower, the volume that it used to occupy increases, because we have the same number of molecules inside of that container, but it's taking up more space because there's less surrounding pressure. And so that process causes cooling. Expansion causes cooling. Has anybody here ever recharged their air conditioner? You know, like the little cans you can buy at the AutoZone? You've done it? So what happened when you were recharging your air conditioner? Do you remember anything unique about the can itself? The can got cold, right. And so if you've ever, the same thing is true, you know, like canned air that you spray out your motherboard with, or if you use enough hairspray, I guess maybe you'd have the same thing. But if you have compressed air in a tank and you let it out, it gets cold because it's expanding. And so the air that's rising is getting colder, and warm air can hold more moisture than cold air can. If you take warm, moist air and you cool it off, then condensation occurs. And so my glasses, whenever I go from like the swimming pool at the YMCA, where it's warm and really humid, and then I go outside on a cold winter day, my glasses are going to fog up. Actually, both directions. There's going to be condensation there because the moisture that was warm becomes supersaturated and then it has to go somewhere. So what are the physical things in the atmosphere that are causing air to rise? The main thing that causes precipitation is air got higher, and so there have to be some physical phenomenon that cause that air to get higher in the atmosphere. And those three, broadly speaking, those divisions are convergence, orography, and convection. And this is a final exam question from a couple of semesters ago. And maybe it'll be another final exam question, like what are the three main causes of air lifting? So we'll talk about all three of those. Again, lifting of air is important because it cools off. And there's something called the adiabatic lapse rate. The lapse rate just tells you how much it cools off by how much elevation you went up. And if air was completely dry and didn't have any moisture in it, then the temperature would change 9.8 degrees Celsius for every kilometer of elevation. So when I visited the Burj Khalifa in Dubai, the observation deck, I think, is maybe around 600 meters. It's noticeably cooler. The air is noticeably cooler up there than it is at the ground surface because you're simply at a higher elevation. If you've ever been into the mountains, you're watching maybe the TV news. It's cooler in the mountains because you're at a higher elevation. This is the slope of that change. For every kilometer of elevation, the temperature is decreasing 9.8 degrees Celsius if the air is dry. If it's fully saturated with moisture, then it doesn't change as much because some of the energy goes into condensing the water. So there's less of a temperature change. So keep that in mind, that all three of these things are all about lifting air and it's becoming more saturated. Now, convergence of the three is the hardest to understand. So we're going to spend a little bit of time talking about convergence. Maybe you've seen maps before of fronts coming together, a warm front and a cold front, or sometimes a high pressure system and a low pressure system. And when the two come together initially, there's just a straight line that divides them. So in this illustration, what we've got is the cold air and the warm air. And you know, the air is not completely mixed when these two fronts initially meet, but there will be some sort of like a turbulence where one of them goes into the other. What it's showing here is that the warm air sort of goes in towards the cool air, and it's actually getting surrounded. This cold air is going to sweep through and start to isolate the warm air. And what it does is it pushes the warm air up on top of the cold air layer. And so as this warm air continues towards the mass of cool air, before they can mix and become the same temperature, that takes a while for them to mix and become the same temperature. Before that happens, the warm air is going to rise up on top of the cold air. And so this cutaway here, this cross section is showing that dashed line AB. So that dashed line AB is a cross section of, here we've got the cold front that's pushing, as it comes towards the warm air, it's pushing that warm air up on top of the cold mass because they have different densities. And so that's why it has to lift upward. And as the warm air goes higher in the elevation, it's becoming supersaturated with moisture, and that's what causes the rain. And so it's not actually the low pressure that causes rain, but simply that low pressure systems are typically corresponding to warmer air that's being lifted. Convergence is sometimes also called frontal lifting, and that's another term that you need to be acquainted with. It's where there's a mixing front that's lifted, and then that leads to the precipitation. All right, let's take a break. We've been going at it for more than an hour now. This is a good pause, stop. We'll come back in 5 minutes and continue talking about lifting. It's probably because also I'm no good at it. I mean, that colors my impression. Okay, so it rains when air is lifted. One reason air is lifted is when fronts collide. There's another reason, and it's illustrated by this picture. This might be Hawaii. Yeah, I think that this is Oahu. All right, so why is it green on one side of Oahu, and they call it the windward side is the green side, and then the leeward side over on the west is actually very brown and almost desolate and desert-like. So why is it green? And we're not talking about any great distance either. I mean, this is probably only 15 miles from one edge to the other. Any guesses on why one side is green and the other is not? Okay. Yeah. Moisture is different on one side than the other. Okay, so you're right to think about the wind patterns. These arrows are indicated when the typical direction of air down there, you know, we expect the wind to be coming from the west towards the east, where, well, Hawaii is much lower in the northern hemisphere, and so it doesn't have that west to east pattern. The pattern that they have there is usually the rain is going from the northeast towards the southwest. So that's the typical pattern, is usually wind is going that direction. Yes? Exactly. Exactly right. Yep, so just what he was thinking that, you know, precipitation is when air is lifted. So there's something that's lifting the air. Here it's a mountain range. So the wind is blowing, that warm, moist air that's coming from the ocean is lifted up over a hill. As it's lifting, it's becoming progressively more and more supersaturated until there's too much and it starts to nucleate, and the nucleated, you know, the dust particles that have moisture on the surface collide, and the droplets get bigger and bigger, and then it rains. But then when that air gets over to the other side, not only has it already rained, but now the water is going down in elevation again too. And so as it goes down in elevation, it's warming up again, and it's becoming, the relative humidity is lower because not only is there less water, but the temperature is higher. And so those are two forces acting in the same direction, that the relative humidity is lower, and so there's a very stark difference. And if you look at the annual precipitation amounts, it may be on the windward side of Hawaii, there can be 90 or 100 inches of rain per year. And on the leeward side of Hawaii, it can be 5 to 10 inches per year. So it's like a tenfold magnitude difference in the amount of precipitation that they've got. So that's called orographic lifting. Orography is just when the clouds are forced to go up over a mountain range or some other obstacle, and because of that lifting, then precipitation patterns are affected. Okay, the third and final kind of lifting that we're going to talk about today is convective lifting. My dad is really paranoid about flying during the summer in the afternoons. He always wants to travel early in the summer because he's been stuck so many times due to the dreaded afternoon thunderstorm. You know, Chicago especially. He never likes flying through Chicago, whether it's the winter or the summer. In the winter, it's because of the snow. In the summer, it's because he's afraid of like Midwestern thunderstorms. And so why is it that you have more thunderstorms in the afternoon than you do in the morning? And it's a fact. You know, if you look at travel delays during the summer, it's 3 o'clock, 4 o'clock, 5 o'clock in the late afternoon that more of these storms occur. What's causing that? And this is showing some picture. The sun is shining, the surface is getting warm, and so warm air rises. That warm, moist air, as it rises, starts to cool off. So we have that process we've already talked about several times already, where as it cools, the relative humidity increases until it's forced to precipitate. But why does that happen in the afternoon? Yeah, there's a daily cycle. So at night, the surface cools, and throughout the day, the surface is warming. And so gliders, you know, as a glider flies, they get these so-called thermals, and that's what causes a glider to continue to fly for hours and hours at a time. It's those same thermals that are lifting air. And sometimes as you're driving across really flat country in Kansas or much of the Midwest, you can see these big clouds. They almost look like mushroom clouds. You're thinking, oh man, was there like a nuclear explosion someplace? But it's just sort of the shape that these clouds take as the air is rising, and then it mushrooms at the top when it's sort of reached the peak elevation that the thermals are going to reach before there's no more driving force for the elevation to increase anymore, because the air has finally come into equilibrium with the temperature of the surrounding air. So the lifted air is at the same temperature as the surrounding air, and then it starts to expand out. That's what gives it that mushroom shape. This is a graph that's showing the lapse rate. As you go up in altitude, the temperature is decreasing, and what causes precipitation is when you have a crossover point between the dew point and the surrounding atmospheric relative humidity. We don't need to go into a lot of details about the dew point, but the point I show you this is just that we could do a graph of temperature versus elevation, and this is the shape that that graph takes. Increasing altitude, decreasing temperature. And so the slope of this line is that 9.8 degrees Celsius per kilometer of elevation. So every 100 meters you go up is approximately 1 degree Celsius in temperature change. The afternoon thunderstorms. My dad would be shuddering. All right, so here is some nice figures from the text that show the growth of droplets. And it starts off with dust particles in the atmosphere. These dust particles have a negative charge on them. The same thing is true of clays. If you remember back to your soil mechanics classes, you'll remember that soil particles that are very, very small have a net negative charge around the outside. And so because of that, particles in the atmosphere, and in water treatment it also turns out, small particles, because of their negative charge, they don't really collide into each other. Under ordinary circumstances, there's a repulsive force there. And so those condensation particles can remain in the atmosphere until they become coated in the moisture that's accumulating on them as the relative humidity is dropping. And then those droplets form precipitation simply when the air movement that would normally be suspending, like the Brownian motion that would normally be suspending those nuclei, is overcome by the weight of the droplets. Impact and aggregation is just the process of the droplets getting bigger. And the snowstorm that we had on Sunday, from 1 minute to the next, there was a huge change in the size of the snowflakes. I was watching the storm out of my window, and at one moment the snowflakes were small, and then 20 minutes later the snowflakes looked like they were huge. And it's all about aggregation and the amount of time it's taking to fall through the atmosphere and the elevation that those droplets are forming at. All right, so that's some of the science of precipitation. Now let's talk about how it's measured. How do we get direct observations of precipitation? Here's a map of some of the gauges in the region, and we'll go to a website in just a few moments to click on each of these locations and see what kind of data it's got. One thing I'll point out is that oftentimes the best weather data you can get is at airports. And so here's the Yeager Airport, here's the Huntington Tri-State Airport, and when you need good weather data, airports are the place to get it because there's usually a long history of data, there's very rarely gaps in it, and they'll take measurements of weather data at airports at much higher frequency than some other spots. Some weather station in the middle of the countryside, it may just be like a daily total of precipitation. Whereas at a nice airport like the Yeager Airport, they may be taking every 15 minutes measuring and reporting the solar intensity of the radiation, measuring the rainfall in 15-minute increments, and so on. So that temporal resolution is important sometimes. This figure is showing in the United States how far back the weather data goes and how many weather stations there are that have that data. Let me make it bigger because this is kind of an interesting figure. All right. All right. So there is weather data that goes more than 140 years, but there aren't that many. It looks like 8. This is a logarithmic scale on the vertical axis. So, we've got 8 weather stations in the United States that go back really far. But there's a difference between recording gauges and non-recording gauges. A recording gauge nowadays is thought of as something that's automated, that is not requiring a person to go out and look at like a graduated cylinder to find out how much precipitation there was during a day. Instead, it's relying on maybe an automatic tip and sensing that tip to record the data. But the general trend is we've got a lot of stations with a short length, a short history, and few stations with a long history. We sometimes want to know about the 100-year storm, right? But here in West Virginia, we may only have 2 or 3 spots where they've actually measured storms for 100 years. And so we have to do a lot of extrapolation and statistical techniques to try and guess at how high the intensity of rain is going to be for some of these long return period storms that are the ones that cause the most trouble. We can say pretty well what the 10-year storm looks like because there are tons of gauges all over the place, but we have 10 years of data. But there's a much smaller number that have long data sets. One thing that's a bit sad is that because of government cutbacks, they're starting to close a lot of weather stations that used to be open. And so that number is actually going down. The number of weather stations in the United States is getting smaller every year. And the same is true of stream gauges as well. One way for us to graph rainfall is with a hydrograph. And I've already used that term for you before. When we are looking at a hydrograph, it's a characterization of intensity of the rainfall. And of course, the hydrograph is the figure that shows the runoff. So we already know hydrograph, and here on the vertical axis of a hydrograph is the intensity of rainfall, and then each one of these blocks represents a duration. This way of graphing several storms is interesting because it's a way of seeing not only when the intensity occurred during a storm. So the steeper this is, that means you have a period of lots of rain during a storm event. But it's also showing you the total amount of rainfall over here on the left vertical axis, the accumulated rainfall in inches. And so you can see that there was a storm on January 8th that had nearly 5 inches of precipitation and had at one point a pretty high intensity. But then the storm on the 24th of July, not only can we see that the amount is lower, but because this is showing the total accumulation over time, we can see when the period of high intensity was. Here on the horizontal axis, it's showing the storm of each time, and the reason it's staggered is just we didn't want to have each of these curves start at the same origin, and then it would be a little bit messy. And so they've been offset by a certain distance, and so each one of them has their own axis. And so the July 6th storm, for example, here is t equals 0 for that July 6th storm. Here is the 60 minutes into the storm for July 6th, and so on. All right. You're practiced at interpreting IDF curves. On the homework assignment I'm going to give you tonight, you're going to get some experience creating an IDF curve from the raw data. You already know that IDF stands for intensity, duration, and frequency. And so the intensity is on the vertical axis. The return period is the fact that you have more than one curve on the figure. And so here's the 2-year curve, which is lower on the spectrum of intensity than a 5-year storm for the same duration. And so the highest return period is always going to be on top. The lowest return period is going to be on the bottom. And then duration is shown here on the horizontal axis. Now, sometimes you will have a linear scale on the rainfall intensity, but it's very common to always have a logarithmic scale on the horizontal axis. The way that you create a figure like that is you go to a gauging station where they've been measuring data for a long time, and you download it from the web. And then you have to rank it. When you download rainfall data, it's usually in a .csv format. And that's kind of just like a generic tabular format that Excel can open up. You can also open it with a text editor. But when you download that data, each row is going to be a different day. And if you sort, having the highest at the top and the lowest at the bottom, that rank order is going to tell you the highest intensity at the top can be corresponding to a certain return period. This Weibull formula is a way of calculating the return period if you have a certain number of years of data. So the total number of years of data is given the variable n. N is whatever row you're on. And I'll show you in a minute. We have an illustration of how we could develop an IDF curve. I think this process will maybe make a little more sense when we look at that specific example. But you repeat it over and over again for each return period. On the homework that you're going to be doing, it's only for a 24-hour duration. And so that's kind of the problem, is you can't download the data for lots of different duration storms. The weather data that we have access to is usually 24-hour totals, and so you'll be calculating what is the intensity for a 24-hour period. Let me show you if we had data that we downloaded over the course of 32 years. We would calculate the return period of that 32 years of data This would be the 33-year storm. The one that's at the top of the list for having the most rainfall would be the 33-year storm, because it would be 32 years of data plus 1 divided by the rank order. And at the top of the list, this is our #1 storm. The biggest one we've ever seen, like for a 5-minute storm, would have an intensity of 12.1 inches per hour. Now, the #2 storm, since we're now dividing 33 by 2, that means the return period associated with this is every 16.5 years on average, you'd see a storm with an intensity of 11 inches per hour. And then the next one, the third row, is corresponding to 11-year intensity. So you'd have to do interpolation if you wanted to know the 25-year storm. You could do a linear interpolation between the 33-year storm and the 16.5-year storm. I'm sure everybody remembers the process of linear interpolation, where we say that we have on one axis would be the return period, and on the vertical axis we would have the intensity, so that if we have here the 16.5-year storm, and we have some intensity that we read off of the figure, and then for the 33-year storm, and we have another, we could find out for the 25-year storm what intensity it should be, according to starting with this and then finding the slope of the line, the change of intensity divided by the change in return period would be the slope of that line. So it's the standard linear interpolation to find the return period in between these data points that you'd calculate. All right, so I want to show you some of these sites that you should be acquainted with and are going to be using for the assignment. The first one, PRISM, is operated by Oregon State, and it's pretty interesting because it has these really nice figures that can tell you how things are going so far. They've got normals, just to give you an idea, over the past 30-something years. Where in the United States is it usually pretty rainy, and where is it usually pretty dry? And you can see down here on the Gulf Coast, they have rainfall amounts that on an annual basis are 60, maybe even 70 inches per year. Along the Pacific Northwest, there are some mountain ranges there that get even more, more than 100 inches per year of rain. Whereas the Intermountain West maybe is having as low as 4 inches of rain per year in Southern California. So that's one of the nice things about this PRISM data, is that they've got these figures that you can find out this month how is the rainfall patterns. And so it'll show you during the month of January, where has there been a lot of precipitation. Alabama and Georgia has been pretty wet this month, 12 to 16 inches of precipitation. California is doing great in the month of January. But then in the Dakotas, it's been relatively dry. Allows you to zoom in. This PRISM data is based on a radar analysis. It's not actually based on gauging stations, but it uses radar, and the grids that they're looking at are these 4 kilometer by 4 kilometer squares, where they estimate how much precipitation there's been based on measurements that the radar is able to take. So it's a really interesting data set. But what we'll use more frequently in design is the Precipitation Frequency Data Server. And so that's put out by NOAA. I really like this one a lot. It's an important data set. It allows you to pick on any state in the United States, and so if we click on West Virginia, then it will take you to a new map of West Virginia, and you can move this cursor around to any spot where you may have a project. And so if we had a project that was maybe near Huntington, I think we can zoom in a bit further even. All right, so let's move the cursor. Did we lose our cursor? All right, let's move it towards Huntington, zoom in. All right, so if I wanted it to be in Ona, I'm going to say, there's my project. And it builds a table down here dynamically. It gives you the option for that to be a table of depth or a table of intensity. And the way that you know the difference is if the depths are increasing with the duration, then that's a depth table. We know that as the storm duration is going up, the intensity is going down, though, right? So these amounts in bold here, 3.5, 5.4, that is in inches how much precipitation you'd expect for a 1-year storm in 5 minutes. Or for a 10-year storm that lasts 60 minutes, you'd expect 1.87 inches of rain. In the brackets, in the parentheses, that's what's called a 95% confidence interval. And all of this is based on statistical regression, and so they don't know exactly how much rainfall you can expect, but through the regression that they've done and the available data, they have 95% confidence that it's within this range. And so if you wanted to do kind of like a worst case scenario, you'd use the upper range of that to do your design within the 95% confidence interval. The amounts are different if we switch this from depth to intensity. Then the trend is that you have high intensity for a short duration storm. So the 5-minute storm, you can see 4 inches per hour, and it's getting lower and lower as the duration is increasing. Because remember, we've talked about before that a storm can't sustain itself at a really high intensity for a long time. The longer the area or the longer the time that's involved, the intensities are lower. Although the amount is increasing, the intensity goes down. There's one more thing I need to point out to you, and that's an option here where you can distinguish between partial duration and annual maximum. Annual maximum is based on what if you have only the biggest storm in every year in this ranked list. Because what they're doing here is they're basically putting together the table for you according to the same process that I've just explained here, where we make the ranked list. Where was that? Yeah, here. All right. So this list, you could filter it and only have in each row the biggest storm during a 1-year period. Or you could have, even if there were 3 big storms in a single year, it would be possible for all 3 of those storms to be in the list. That's the difference between partial duration, which is, I think, the more accurate approach, and annual maximum is you're filtering the data so that you only have 1 big storm per year. But we all know that that's not true. You can have more than 1 big storm per year, and so I think it makes the most sense to do your design and analysis based on partial duration. And that's the default option that comes up, is partial duration. So this is a really great website, the Precipitation Frequency Data Server, because of the flexibility, and they've done all of the statistical analysis, and there's a whole book, a very lengthy book, where they explain how much data goes into the charts and how they've changed over time. And this NOAA Atlas 14 is a publication that's been revised every 10 or 15 years as new storm data becomes available. They have to analyze whether their past estimates have been high or low. So it's really interesting. The NCDC is where you can go and click on an individual gauge station and get the raw data. You're going to have to do that on the assignment. Go get the raw data for a site. And so let me give you the handout, and you can take some notes on this handout as I show you how to get to one of these actual data sites. So when you get there, you'll go to Data Tools, and there's so much data available, you kind of have to filter it and narrow things down a little bit. Otherwise, you'll just be buried in the data. And we are going to search a location. Let's see. Okay, so find a station. I'm going to just type in Huntington. And it zooms in automatically on Huntington a little too tightly. Let me zoom out a bit. And then when I select a data set, I'm going to have daily summaries is what I want. And in those daily summaries, I'm specifically looking for precipitation. And the last thing I have to do is tell it the range that I want data for. And so if I want data that goes back to the 1980s, for example, I could, on this box here, I say 1980. So from 1980 until the present. And so any stations that has data within that range is going to pop up. And there's a lot of them. But if you hover over it, you'll notice that some of them don't have during the full period. So here's Hamlin, West Virginia. And this is one of those sites that goes way back, 1899. Some of their precipitation data goes back to before the 1900s. But it's only during 63% of the years. So that means that maybe someone forgot to record one day, or somebody stopped recording for a few years, or they weren't confident, like maybe it turned out when they calibrated an instrument that between calibrations it was giving bad data, so they had to just throw out all of the years in between, because this only holds on to the audited, like fully verified data. So this is a pretty good data set, 63%, but if you go to the airport, for example, you'll notice that the data quality is even higher. Let's see, here's the airport, I think, right there. I click on that, Huntington Airport, 100% coverage from 61 until 2017. So that's a good spot. After you add the data to the cart, you don't actually have to pay for it. It's free. And it's changed. I think the way it works is that once you put it in your cart, then they'll send you an email when it's ready to download. Like it takes a few minutes for one of their servers to archive all of the data into a zip file, and then you get an email notification when it's ready. All right. Sometimes people make a mistake of taking data from a weather station that's near their house and assuming that the same thing is going to happen in one location as in another. So let's take, for example, Huntington Tri-State Airport compared to the weather that I measured at my house in Ona. They're about 20 miles apart. I had a rain gauge that's a calibrated good research grade rain gauge, and that's the blue line here. And I started measuring precipitation at the same time that precipitation was measured at the Tri-State Airport. And so you can see for a little while, the Tri-State Airport was ahead, and then there was a storm where this storm, it looks like it didn't rain at all at the airport, but it was a pretty considerable storm out in Ona. That vertical line means that there was a storm that day. Periods of horizontal just means no additional precipitation. Vertical, it rained, but it didn't rain at the airport. Here's a big storm that occurred at the airport, but it was relatively small in Ona. And so this is illustrating the idea of spatial variation, that just because it's raining in one location doesn't mean that it's raining in another. There can be, in addition to just that spatial variation, there can be are differences that arise out of, like, if storms are causing the rain to come sideways, and if your stream gauge is, if the rainfall is being intercepted by structures or plants, then that can be a problem. Also, rain gauges are supposed to be up off the ground, and so if there is if it's raining so hard that it's splashing from the ground, it can get back into the gauge, sort of like bouncing. The raindrops can actually bounce up from the ground into the rain gauge, and so that's why they're generally elevated off of the surface a bit. So if we have a series of gauges in a variety of locations, and let's say that this boundary represents the watershed, you know, that area that we know there are streams in there, that because of the ridge lines, all of the flow within this area is going to be concentrating to a spot that we're interested in. Well, one approach to taking a variety of different stream gauges is just to do a simple average, an aerial average. So here, it looks like there's 1, 2, 3, 4, 5 different rain gauges inside of the watershed. And they took some rain gauges that are near the watershed as well. They included more than just the 5 that are in the watershed. So if you just take sort of a weighted average for this watershed according to the aerial approach, it would be 3.26 inches. A more sophisticated way to do that, though, the Thiessen method, says let's divide our rain gauges into contributing areas. And so what you do is you draw lines between where gauges are. So look at Big Creek and Wyatt. If we have a line connecting those two, then this thick black line is between them, and it's perpendicular to the line that connects them. And so you draw a lot of these thick lines, and each one of them is just between two gauges. So Hangtree versus Upper Falls, that line is just even between them, and so that when we do enough of them, here's the one between Foster and Hangtree, then all of the area inside of that boundary would be assigned the precipitation amount associated with the gauge inside of it. And so Hangtree, we'd measure this area, and we would come up with a weighted average, and you'd multiply the area of that station by the intensity or the depth at that station and come up with a weighted average according to the Thiessen method in that way. So that gives you a better idea than just the arithmetic mean, because why should we include this Emmettville when it's not even inside the watershed? And the thing that the gauges that are closer to the watershed should maybe have more weight. So an even improved version above and beyond the Thiessen approach, this isohydal, is saying, let's come up with contour lines to represent intensities. And these contour lines, we do the same thing of, here is the 9-inch contour line, here's the 6-inch contour line, and just by kind of interpolating between the 4.13 and the 9.10, you'd say here's 5, 6, 7, 8, and so there's 9. And you try and do your best to interpolate between them where the rainfall was actually measured, and you come up with these bands of about what the intensity was and assign them to the corresponding area. And this is just another way of coming up with a weighted average of how much precipitation was inside of an area. When you're doing watershed modeling, you can use any one of these approaches. The preprocessors that we have access to for watershed modeling can use Thiessen, they can do isohydal, or there's several others as well. All right, I think this is the last slide. No, wait. For what's printed, I have to remind myself where the printed handouts end. Oh, we still have the probable maximum precipitation. That's important. All right. We've seen this figure when we were looking at the Oregon data. Temporal distribution is variations in seasonal, like when do you have a rainy season versus a dry season. And so there are parts of the country where they have a lot more rain. Like if you look at Boston, it's pretty consistent through the years. January, February, March, April, May. It doesn't matter through the year. There isn't like a specific rainy season, but that's different than the patterns in San Francisco. In San Francisco during the summer, there's a lot less precipitation. You can see here that the precipitation quantities is lower than it is in the winter. So temporal distribution is just talking about variations over time. There are spots where it rains a lot of the time. Down in southern Florida, you may have 80 days per year with thunderstorms, whereas in parts of the west there may only be 10 or 15 or even fewer days that have thunderstorms. And so where you're doing a project, you have to be sensitive to how there's variation in both space and in time. If you're designing something that has a really, really low tolerance for failure, like a dam, we don't want dams to ever fail. We can't design them with the 5-year storm or even the 100-year storm. If a dam fails once every 100 years, then that means 1 out of every 100 dams is going to fail each year. Okay, so when we're doing like these really high-risk analyses, we want to find out what's the maximum precipitation we could ever expect to see in an area. And that's not done by observing the data from that area, but it's looking at extremes from over the entire globe. And this is a really interesting figure that's showing like the most rain that's ever been measured for a storm that lasted 1 minute. So there's some place in Guadalupe where they had a storm that was nearly 2 inches of rain that came from the sky in 1 minute. And they did that same thing all over the world. They've measured how much rain could you expect in a storm that lasted 30 days. And there's this place in India where over a 30-day period they had 400 inches of rain, that's kind of a lot. And then it turned out that when they put it on a logarithmic x and y axis, the data kind of followed this trend. And so doing this linear regression, you can in millimeters or inches estimate based on how many days you're putting in the amount of rainfall. Is this H? It may be, D is in hours. The point is that that we have to think beyond the available data and have a much larger extrapolation. And in the United States, there's a publication called HMR 41 that predicts the maximum probable precipitation, the PMP, probable maximum precipitation, and it varies based on the size of your watershed. And remember that general principle is that the smaller the watershed, or the shorter the duration, the higher the intensity can be. So these are storms. In each column, it's the duration of the storm. But you can have over a 10 square mile area, you may see 24 inches of rain over over a storm that lasts 6 hours. Does anybody know for West Virginia how many inches of rain we usually see in a year, just for comparison? Our average in West Virginia is about 45 inches per year. So that's in a typical year. What this figure is saying is that you could, in 48 hours, in 2 days, in a 10-mile square area, you could have as much rain as we usually get in an entire year. But then as the area is getting bigger, the intensity is, the amount is getting lower because that's an average over the entire basin. So it's very unlikely that if we have a 10,000-mile area, that it's cloudy over that entire area. You know, it may be cloudy in one spot and sunny in another. And that's why these rainfall amounts are going lower and lower as the watershed area is getting larger.
Yeah, what did these letters stand for?
Oh, the notes? I think that they're probably telling you what the data is based on, like specific storms that were occurring, like the origin of the regression that built this data. Good question. So you, in the same way that you could plug an IDF table into Q equals CIA, you could also, if you need to, do an analysis based on the probable maximum precipitation, so like the worst case scenario. how much rainfall is going to be coming out of an area. That spatial distribution effect is estimated in our book. It's showing the percentage of rainfall that you'd expect to see as a fraction of the average. And this is a little bit hard to understand. So for a 24-hour storm, a storm that lasts a long time, it would be unusual to see any more or less than like 90% of the aerial average to be 100% is like the typical rainfall patterns. And so you can get, for a short duration, further away from the typical patterns, but for a long duration, it's going to be less spatial variation. And the larger the watershed area is, so here on this on the horizontal axis, the watershed area is getting bigger. The curve is flattening out because as it gets larger and larger, it's unlikely to have an even bigger deviation from the typical rainfall patterns. This figure isn't the best. I think that probably just looking at the raw data itself helps to understand the trends better. That the trend is smaller amounts with increasing size, and then obviously as the storm duration gets longer, so does the amount increase, though there's diminishing returns there. Going from 6 hours to 12 hours doesn't double the amount. It's less than double the amount. You can see here it went from about 25 inches to just 30. Because the longer the storm duration, it's becoming increasingly unlikely that you're going to have that same high intensity of a storm for a full 3 days. So they analyzed a bunch of storms and found that there are typical patterns in the United States. And they categorized different storm types according to the geography of the U.S. And a type 1 and type 1A storm is typical in the Pacific parts of the United States, where in a type 1 and 1A, the rain is relatively steady. Like they don't have as long of a high intensity. These curves on this horizontal axis, it's showing the time. And so at the end of the 24 hours, you have 100% of the storm that's occurred. And what this is showing is that, for example, in a type 2 and a type 3 storm, it starts off slow, but then this period where most of the rain happens, most of the precipitation occurs in a very short period. Whereas they say in like Seattle or San Francisco, it's just sort of a slow, steady mist. The water's just, it's kind of raining all day a little bit, but there's not as much of like that huge peak that occurs. And that's partly because of what's causing the rain. You know, here in the areas where we've got type 2 storms, this is the land of the afternoon thunderstorms. The Gulf Coast is having a lot of storms that are influenced by hurricane patterns, and the same is true of a part of the east coast of the United States, that they're susceptible to hurricane and tropical storms. But here in West Virginia, we're fully inside of the type 2 region. And so by type 2, what we can do is we can find out how much rain to expect during our design storm and know the intensity over time. When we get to watershed modeling, we're going to use this table, and you get an amount. Let's say you have a storm that's 5 inches in depth. Multiply by the fraction for each one of these. Here in West Virginia, we're type 2. So that says that the total amount up until 2 hours would be 5 inches times 0.022. Now, by the end of the full 24 hours, it's 100% of the precipitation has occurred. But this table is just kind of a digitization of this curve. And it's telling you what's the intensity at any given time during the storm and what's the total amount of water that's occurred during any part of the storm. There are also 6-hour storms that are sometimes used for design, just to find out what the hydrograph might look like. There's some figures in your book that are similar to this that shows contour lines of typical storm patterns. And so There's a figure in your book that shows the 2-year, 60-minute storm, and if you're asked to find the precipitation in Chicago, for example, you just find Chicago on the map, and you'd sort of, from these curves, find out for the 2-year, 60-minute storm how much rain you could expect. And there's another figure in the book that shows the 100-year, 60-minute storm, and you find your location, and you'd interpolate between these contour lines and find the amounts. But there isn't a map like this for every return period and every storm duration, because you can interpolate between them. Once you have the 5-minute storm and the 15-minute storm, then you could interpolate and find the precipitation depth for the 10-minute storm. And the same thing is true for the 30-minute. You can use the 15 and the 60, and averaging between them according to this formula, you could find out the precipitation amount for the 30-minute storm. Now, if you have the 2-year and the 100-year storm, then you can find the depth for other return periods as well. And you may remember that I showed you something similar to that when we were using StormCAD, that you can put in the design depths for a couple of storms, and then it will just create the IDF curve for you for all these other return periods. And so that's why in your book it only has a 2-year table and a 100-year table, is because you'd be expected to then use this regression formula to interpolate and find the depth associated with storms of other return periods. All right, I'm starting to lose my voice, and so we need to wrap this up pretty quickly. I wanted to emphasize the difference between rainfall amount and rainfall depth. And sometimes people will confuse the two. When we're talking about the rainfall amount, that's a volume. And the way that you calculate that volume is by multiplying the area of a catchment by the depth that occurs. And so if we're measuring the depth of storm, whether it's millimeters or inches, and multiply it by the area, and that's how you get the volume. It's also important to keep the difference between rainfall intensity and rainfall depth, or rainfall amount, separate. The intensity is always going to have a time component in the units, whereas the rainfall amount or the rainfall depth won't have a unit of time associated with that. And remember, in the case of recurrence interval, when we're talking about a high return period, a 100-year return period is going to have a low probability in any given year, and it's an inverse. And so a 100-year storm is going to only have a 1% chance of occurring this year. A 50-year storm would have a 1 in 50 chance, or a 2% chance of happening in this given year. You could have 2 50-year storms in 1 year. It is statistically possible. It's just less common and improbable that you'd have lots of big return period storms in 1 year. Let's skip over this. One last picture to look at, and that is the map of precipitation patterns in West Virginia. And it shows that it's in the high mountain areas that we have the highest precipitation amounts, see, upwards of 64 inches per year. But out here in Cabell County is a relatively drier part of West Virginia, and the reason for that is related to elevation. You know, it's in the high elevations that they have more of the orographic lifting than we experience here in Cabell County. Any questions? All right. I've tried to give you some instructions on the homework to make things straightforward, but this is going to be one of those assignments where you know you're in graduate school. You know, like the difference between undergrad and graduate school is that when you have an undergrad homework assignment, probably you saw an example in class that was basically the same, and now you're just applying it yourself. But sometimes in graduate school, you have to get more comfortable with self-directed learning. And so, for example, I asked you to use the same kind of idea behind these maps. You have some homework problems. Some of the book problems are related to finding the precipitation amounts at different points on the map. And we didn't do any of those, but I tried to talk you through the general idea. If you run into trouble as you're working on the assignment, feel free to stop by my office or send me an email and I'll do my best to help you out. Otherwise, I will see you next Wednesday, and I'll post those quiz scores as soon as I finish grading it. Take care.